A tape measure is one of those tools that disappears into habit. You pull it from a belt clip, extend the blade, hook it on an edge, read a number, let it snap back into its case. It feels mechanical but uncomplicated. In reality, it is a compact negotiation between physics, portability, and human imperfection. Before the retractable tape measure, measuring tools were either rigid or soft. Folding rulers made of wood or metal were common in carpentry. They consisted of short, rigid segments connected by hinges. They were durable and accurate, but limited in reach. To measure a longer distance, you had to reposition them repeatedly, introducing potential cumulative error. Cloth measuring tapes existed as well, especially in tailoring. They were flexible and compact. They could wrap around curved surfaces, but they stretched over time. They sagged under their own weight. They were not ideal for spanning horizontal gaps. The problem was clear. Builders needed a measuring tool that was long, portable, and rigid enough to extend outward without support. The breakthrough was not just flexibility. It was spring steel. In the 19th century, advances in metallurgy made it possible to manufacture thin strips of steel that were both flexible and resilient. These strips could bend and then return to their original shape without permanent deformation. That property made retractable tapes possible. But flexibility alone was not enough. A flat strip of thin metal, when extended horizontally, would droop immediately under gravity. The aha moment in tape measure design comes when you look closely at the blade's cross-section. It is curved. That slight concave arc across its width transforms the blade into a shallow beam. In structural engineering, curvature increases stiffness. A curved sheet resists bending far more effectively than a flat one of the same thickness. This means the blade can extend several feet outward before collapsing. The curve is not aesthetic, it is structural reinforcement. If you flatten the blade, its ability to stand out unsupported disappears. The arc is carefully tuned. Too shallow and it loses rigidity. Too deep and it becomes difficult to retract smoothly into the case. The blade must also balance thickness and flexibility. Thicker steel increases stiffness and durability, but reduces ease of bending into the case. Thinner steel retracts more easily but risks kinking or tearing. Inside the case lies another critical element, the recoil spring. When you pull the tape out, you are winding a flat spring tighter inside the housing. That spring stores mechanical energy. When released, it unwinds, retracting the blade. The tension must be calibrated carefully. Too weak and the tape retracts sluggishly. Too strong and it snaps back dangerously, potentially cutting fingers or damaging the hook. The snapback behavior is not merely convenience, it solves a portability problem. Without retraction, a long measuring strip would require manual winding or folding. Retraction allows quick deployment and storage in a compact case. But the most overlooked detail sits at the very tip, the hook. The hook is attached with small rivets and it moves slightly. That movement is deliberate. The thickness of the hook itself would introduce measurement error if fixed. When you hook the tape onto the edge of a board and pull outward, the hook's outer edge defines the 0 point. When you push the hook against a surface to measure an interior space, the inner edge defines the 0 point. If the hook were rigidly fixed, one of those measurements would be off by the thickness of the hook. Instead, the hook slides back and forth by exactly that thickness. When you pull, the hook shifts outward. When you push, it compresses inward. That small sliding motion compensates automatically, preserving accuracy in both directions. This is a subtle but profound design solution. It acknowledges that users measure both external and internal distances and that human technique varies. The tool corrects for its own material presence. The printed numbers also reflect design choices. The markings must be legible in low light and resistant to abrasion. They are often printed or etched with protective coatings. Some tapes include standout markings at standard construction intervals, such as stud spacing, reflecting real-world use cases. Even the width of the blade is chosen carefully. Wider blades increase stiffness and visibility, but require larger cases and stronger springs. Narrower blades fit into compact housings but lose structural stability. Tape measures designed for professional construction often feature wider blades to maximize unsupported extension distance, known as standout. Standout is a performance metric. It reflects how far the tape can extend horizontally before bending. The case itself is shaped for grip and durability. It must withstand drops, impacts, dust, and moisture. Rubberized exteriors improve handling. Internal shock absorption protects the spring mechanism. There is also the matter of locking mechanisms. Most tape measures include a thumb-operated lock to hold the blade in place. This allows one-handed operation and stable reading. The lock must apply enough friction to prevent slippage, but not so much that it damages the blade over time. Every detail responds to human behavior. Carpenters often measure alone, stretching the tape across long spans. They need the blade to remain extended without assistance. They may hook the tip on an edge and walk backward. The curved blade and sliding hook make that possible. There is also the issue of environmental exposure. Steel expands and contracts with temperature. Over long distances, this can introduce slight measurement variation. High precision tapes account for this with calibration and material selection. However, for most practical construction, the variation is negligible compared to human handling error, and that is another key point. Tape measures are designed not for laboratory precision, but for field reliability. They tolerate dust, bending, impacts, and imperfect use. The numbers are large and spaced clearly because they must be read quickly. Some tapes include fractional markings down to small increments. Others simplify for speed. Trade-offs appear everywhere: durability versus cost, precision versus usability, length versus compactness. The retractable tape measure represents a resolved compromise. It replaced folding rulers by offering greater length and faster deployment. It replaced cloth tapes by offering rigidity and repeatability. It became the standard because it adapted to dynamic job sites and human variability. The moment of realization deepens when you consider how many forces it negotiates simultaneously. Gravity tries to bend the blade downward. The curve resists. Material thickness tries to introduce measurement error at the hook. The sliding rivets compensate. Stored energy in the spring tries to snap the blade inward violently. The case and lock regulate release. User impatience tries to misread numbers. Bold markings reduce ambiguity. A tape measure is not just a strip of numbered steel. It is a portable beam, a calibrated scale, and a tension spring system contained within a palm-sized housing. Invisible design reveals itself in correction. The tool anticipates mistakes and neutralizes them. It accounts for its own thickness. It fights gravity. It retracts for safety. And yet, it feels ordinary. You pull it out without thinking. You let it snap back, but inside that snap lies coiled potential energy engineered to last thousands of cycles. The curve in the blade, barely noticeable, is doing structural work every second it is extended. The sliding hook, moving only a few millimeters, is preserving measurement integrity in both push and pull scenarios. Invisible design is often about quiet compensation. The tape measure compensates for gravity, for material thickness, for human inconsistency. It turns a flexible strip into a stable measuring beam. It turns stored energy into convenience. It turns potential error into automatic correction. And when a design reaches that level of resolution, it becomes difficult to imagine it any other way. The tape measure feels inevitable, but inevitability is usually the result of refinement. A century of small adjustments, curvature, spring tension, hook play, shape the form we now take for granted. A compact tool that fits in your hand, capable of stretching across rooms, resisting gravity, and correcting its own physical presence. Not flashy, not digital, just precise enough, durable enough, and intelligent in the quiet ways that matter. That is the signature of invisible design.